Good afternoon. In today's session, we are supposed to study about the exponential increase of output signal to noise ratio. So, in previous session, we have seen about the block diagram of pulse code modulation, in which we are using the low pass filter to convert analog signal into a digital form. So, firstly, we will need it to first sample the signal. So, here the practical signal are time limited. So, they will have infinite bandwidth, and the sampling frequency we will require to sample such signal will be infinite. So, in order to limit the bandwidth, we can say that as a W hertz. So, if we want to pass the signal, that is nothing but the time limited, hence we will require infinite bandwidth through a low pass filter. So, we can say that filter as an anti-alias filter. So, here we will not lose the information from the original signal. After that, we are doing the sampling. It means what? Low filtered analog signal now will get sampled with the sampling rate. That will be above Nyquist rate. It means what? Here you will get Fs that will be greater than 2W, because we are saying we will require the frequency that will be above Nyquist rate. So here sampling process will give rise to the train of samples, because it will give us the samples with the amplitude depending on the instant of sampling. So here we will get the sample. Now we are supposed to convert that sample into a bit stream, because we will require the digital. So we need to limit the number of level of that sample signal. So for that we will require quantization. It means what? Here we are supposed to do approximation of a continuous analog signal by taking signal which will having the discrete amplitude from a available set, because here we are supposed to do quantization which is assumed to be memory less and instantaneous. It means what? Less means quantization of current sample does not depend on its past value. So here when we are supposed to do quantization, the quantizer can be uniform or the non-uniform. We have seen this concept. In uniform quantization, we are doing the representation of the levels that are uniformly spaced. And in non-uniform quantization, we are taking the approximated level which are spaced non-uniformly. It means what? Here we will get the characteristics of quantizer that can be mid-range or that can be a mid-rise. So here now when we are doing the quantizer, at that time, if there is no input to the quantizer, at that time the output of mid-range will be 0, and we will get the output of the mid-rise that will be plus than equal to delta by 2. It means what? Here we will get the number of quantization level in the case of mid-rise will be even, but for the number of quantization level for the mid-range that will be odd. So here after that we are doing the encoding. So we can do that encoding in the binary code, ternary code or the M-ary code. Binary means what? Which will represent that quantized signal that will have the amplitude only 0 and 1. Ternary means it will represent each quantized level into 3 levels, and if that represents each quantized amplitude will be into M levels, that will be more than 3. We can say M-ary code. So here if we are doing one-to-one correspondence between the representation level and the code word, at that time we are using the 3-bit PCM, that is nothing but 2 raised to 3, that will be have 8 quantization level. So here we can divide our amplitude signal into a 8-bit. So here the number of bits required for encoding, how it will depend on the number of quantization level. It means what? We can take L equal to 2 raised to V, or you can take, if you are taking the log, you will get V equal to log 2 of L. Already we have seen this concept when we have seen about the quantization. At that time, what we are saying, the number of bits required for the encoding the sample. That will depend on the number of quantization level. So if we are taking the quantization level as L, the number of required bits we can take as a V. So you can take L equal to 2 raised to V, or you can take V equal to log 2 of L. These equations you will be needed to solve numericals. So when we are doing the regeneration, we will get regeneration by reconstructing the PCM signal by means of chain of regenerative repeaters. So it will do reshape the distorted signal into a clean pulses. So we can do regenerative by doing equalization, by using clock recovery, and by doing the decision making. So at the receiver we have seen we are using the decoder. It means what? Here we are supposed to take regenerative received pulses, and these we are supposed to regroup into a code words, and we are supposed to decode that into a quantized level. It means what? The decoding process involves the generating a pulse whose amplitude is linear sum of binary values 0 and 1 in the code word. So we can say that as a digital to analog conversion, because at the output we will need the value that will be analog. So here when we are introducing the quantization error in the PCM signal, we can say this is because of we are taking the sampled output that will be approximated to the nearest value. So here we will get the output signal to noise ratio. So we can say when at the receiver we will get the signal to noise ratio if input signal is sinusoidal. Then we can take signal to noise ratio that will be equal to 3L square by 2, or you can take that as in the form of M of t, the original signal, and the power MP. So you can take as S naught by NQ equal to 3M square of t upon MP square into L square. Here we are saying the number of level, these are nothing but L, and what we have seen, these are depending on, we have just now we have seen, if we are saying the number of level N, we can take that like L square equal to 2 raised to N, or you are saying N equal to log 2 of N. So here is the number of bits to generate the L levels. So here we can take our signal to noise ratio that will be S naught upon NQ equal to 3M square of T upon MP square into L, you can take as a 2 raised to 2N. So you will get here L square will be 2 raised to 2N. So here using the expression for the bandwidth, you will get here Bt equal to Nb. Then we will arrive at signal to noise ratio SQ of NQ equal to 3M square of T MP square 2. Now we can write N Bt by B. So you can write 2 Bt by B. Taking the logarithmic on both sides, you will get dB value here. So S naught by NQ dB 10 log 10 S naught NQ. Bt 2 raised to 2 Bt by B. So now when we solve this, you will get 10 log 10 3M square of T MP square plus 10 into 2 and log 10 2. So you can get here the value alpha plus 6n dB. So here now we can see one numericals that will be on the signal to noise ratio. So given sinusoidal modulating signal M of T, the sampled signal of amplitude AM into a load resistance R 1 ohm. Find the signal to quantization ratio, or we can say that is the SNR. So now what we are having the equation? We are having the equation 10 log 10 S naught NQ equal to what we are having? Alpha plus 6n dB. So here now you can take P average equal to AM square upon 2. If we are setting M max equal to AM, you can take AM equal to M max. So you will get S naught upon NQ equal to 3M square of T upon MP square into 2 raised to 2N. So now you can write Here we are having m max equal to am, and we are having am square equal to 2 into p average. So you can write a equal to square root of 2 p average. So here we are having the now m square of t. So you can take that value as 3 p average upon m square max into 2 raised to 2n. If you solve, you will get 3 by 2 into 2 of 2 raised to n. So if you solve for the like alpha plus 6n dB, you will get 1 plus 1.76 in plus 6n dB. So here we have seen how we are taking the level and n at that time, how you will get the signal to noise ratio, you can see in this table. So here now we are supposed to solve some examples that will be on the PCM. You can see here. If we are having the question, we are given a signal m of t 2 cos 2 pi into 250t as a single tone signal input. We are supposed to find signal to noise ratio when there is a 8-bit PCM. We are having signal to noise ratio that will be P average upon NQ. P average you can write as a 2 by delta square. So now we are having for 8-bit encoding L equal to 2 raised to n. They have given 8-bit. So you can take n equal to 8-bit. So 2 raised to 8, you will get 256 level. L is nothing but the number of level. You will get number of level equal to 256. The amplitude AM of sinusoidal wave means that we will get here MP equal to 2 because they have given 2 cos. You will get 2 holes. So the total signal swing possible minus MP to plus MP. MP is 2. So here we will get will be 2 MP. 2 MP is nothing but 2 into 2, 4 holes. Therefore, average signal power is AM square by 2, 2 square. 4 by 2, you will get 2 watts. So, the interval delta is nothing but 2 MP by L because we are having the formula, you can see our previous slides. So, here we are having the formula, we are having all values. So, you can put 2 MP, we are having 2 MP is nothing but 2 into 2, 4. 4 upon L. L how we are having 256 level. So we will get 4 upon 256. If you solve, you will get 1.5625 into 10 raised to minus 2 volt. Now we are supposed to find signal to noise ratio. We are having the quantization noise NQ. NQ is nothing but delta square by 12. So here if we are taking P average equal to 2 W, SNR will become P average upon NQ. S naught upon NQ equal to P average upon NQ. So here you can write 12 into 2 upon delta square. 12 into 2, 24. Delta we are having value 1.56 into 10 raised to minus 2. You are supposed to take square. So if you solve this, you will get 98.304. If you are taking in dB, you can take SNR dB 10 log 10 log 10 log 10 98,304. If you solve, you will get 49.93 dB. These types of numericals you will get in the exams. So here firstly we will see one example. Again we will go to the differential pulse code modulation. So firstly we will see the example. We are having the signal m of t equal to 2 cos 2 pi 250t. The same equations, only the values are changing. M of t 2 cos 2 pi t as a signal input. Here what is the question? If the SNR to be at least 36 dB, there we are supposed to find the SNR. Here they have given the SNR. How many bits n are needed to encode the signal? Here we are supposed to find small n, number of bits. Other parameters such as signal power remains the same as we have taken in the A, जो अभी solve किया था. So now here we are having the formula. How we are having 2 raised to n equal to L. So firstly we are supposed to find L. How we can find L? L will be depend on, because we are having the formula for L. L is nothing but 2 MP upon delta. It means what? Here firstly we are supposed to find MP. We are supposed to find delta. How we can find? So see here. Now we are having the value for the SNR 36 dB. So we can take that as in the value. So if we are taking anti-log, you will get 3981. So remembering that we are taking the interval delta equal to 2 MPL upon 2 MP upon L. So now we will get 2 MP equal to delta into L. So you will get the value 4, because here we are taking the MP 2. So 2 into 2 you will get 4 volt. Now we are having the SNR, so you can write SNR 3981 equal to 2 MP upon delta square. 2 MP you will get 4 upon delta square. So you will get delta square equal to 4 upon 3981. If you solve, you will get delta value that will be 0.0317 volt. Or if you are taking, you will get 0.001005. Therefore, now we can determine the value of the number of level to find the value of L. If you find number of level, we are having the formula L equal to 2 MP upon delta. 2 MP 4. Delta just we have solved 0.0317. So you will get number of level 31.5. Now we are having 2 raised to n equal to L. 315.5 you can take as a 32 approximate value. So we are aware 2 raised to 5 that will be 32. So here you will get small n equal to 5. So we can say the lowest integer number of bits that will give at least 31.5 level is n equal to 5. So here we will get answer that will be the 5 bit. Differential pulse code modulation we will see in the next session. Thank you.